Kia ora koutou. This video is for people in 13 MCA who are getting ready for the AS exam, and for people in 12 MCA and Ben, Tosef and Snehal who have just done this paper in the school exams last week. So what I'm going to do is over a few videos just go through the Pure 1 paper that you did, which was from March 2020. So in this video we've got the first 4 questions, I think, depending on how slowly I end up going. In the first one we're given a function, and this is the function here. And it's defined when x is less than -1, and we have to say if f is an increasing function, a decreasing function, or neither. So to figure out whether something is an increasing function or a decreasing function, what we're looking at is what is the gradient of the curve in a particular region. So here we need to be looking at the whole function, which is defined when x is less than -1, and we're asking, does it have a negative gradient, in which case it's decreasing, or does it have a positive gradient, in which case it's increasing? So step 1 is to differentiate the function and then to figure out what we can about the sign. So the function is rewritten like this. First of all, we give that a negative power to make it easy to differentiate. The gradient function will be negative 3x plus 2 to the -2 times the derivative of the inside function, which is 3, and then plus 2x. So let's rewrite that now as -3 over 3x plus 2 squared plus 2x. So that's my gradient function. Important to remember here that x is less than -1. So why does that help me? Well, it helps me because 3x plus 2 squared is always going to be positive, greater than or equal to 0. And that means that -3 over 3x plus 2 squared is always going to be negative, right? Because it's a negative number over a positive number. And we also know that 2x is going to be negative. So that means that I've got f dash of x is made up of one negative number plus another negative number. So f dash of x is less than 0, which means that the function is decreasing. That's all we have to do, right? We're just looking at the gradient and what is its sign. On to question 2. Okay, so question 2 is one where you have to be quite careful with your language. You're told that you've got a graph. The graph is of the function f of x, so y is equal to f of x, and it's transformed into y equals 1 plus f of a half of x. So when you're doing these questions, I find it useful sometimes to just work with a really basic function that we know well, and that will help us see what's going on. And we just have to be quite precise with how we describe the transformations. Now the easy one in here is the +1. We know just intuitively that it's going to move the whole graph up by 1 unit. So how do we say that nicely? So y is equal to 1 plus f of a half x. So the first transformation is that the function is shifted or translated. Either of those words is fine. Shifted or translated upwards by 1 unit. And we want to always say whether we're talking about the x or the y direction. So by 1 unit in the direction of the y-axis. Okay, something like that, right? If you want to, you could draw, you have to describe it, but you could draw like this, showing that it's going up by 1. But you must have the words. Now the second one is the one that's slightly muckier to work with. So this is where I think if you put in an example, let's start with a basic parabola, y is equal to x squared. Now what happens if instead of putting x into my function machine, I put in a half x? Well, I'm going to have a much broader parabola. So if I start with that one, then a quarter x squared is one that looks like that one there. And that's a stretch function. All right, so what we want to say here is that the second change, so the first change was shifting up 1. So the second one is that the function is stretched. And then we have to talk about the stretch factor. So it's stretched by a factor. 2 ways to do this. The easiest way to do it is to say that it's stretched by a factor of 2 in the x-axis, or in the x-axis direction, or something like that. Maybe just in the x direction. And what that means is that every value that we had to start with here is doubled in this direction. So the y doesn't change. I guess the other way you could talk about it is that it is vertically stretched by a factor of 1/2 in the y direction. But that's actually not quite right here. So yeah, okay, so I would definitely go with a factor of 2 in the x direction. I haven't thought too much about that. That is, I mean, that's kind of the obvious two transformations to describe there. Make sure you've got the language of translation or shift, and of stretch, and of talking about the direction of the axes. The next question is a volumes of solids of revolution question, but the difference is that we're rotating something around the y-axis. So let's have a look at the question. We've got a shaded region, but it's enclosed by the curve and the y-axis, and the line y equals 5, right? So this is what we're taking, and we are going to spin that around here. So we're going to make some kind of nice pottery object, and we're going to find the volume of it. So let's go back to basics and look at an easy example where we're not working with the y-axis, just in case anyone watching might have forgotten how we're doing volumes of solids. So in general, suppose that I've got this curve here, and I've got two values, a and b, and I've got a function which is f of x. So that could be, I don't know, maybe it's, well, it's whatever, because this curve is a silly curve. If I want to make that into a volume of solid, what I'm doing is I'm spinning it around, and that means that I'm going to have a whole series of circles that are going to make up my shape, and those circles are infinitesimally small. But you can visualize that if you turn this into some kind of pottery object, right? So suppose we've got that. Now just pretend that that's symmetric. Every single layer there is a circle, and the circle is going to have a radius which is equal to the height of the curve. And we're going to take those circles and we're going to add them up. And that's why you don't get given the formula for volumes of a solid in AS, because we want you to think about it as adding up, which is an integral, that's all integration really is, the circles, and the circles are given by pi r squared, and so the radius is the height of the curve, which is f of x. So that's my formula for the volume of solid of revolution. So when we're doing that around the y-axis, it's going to be the same thing, except here what we're going to have is that the volume is going to equal the limits between 5 here and 1 here, and it's going to be pi times the radius squared. But the difference is that we're working this way. So before we wanted to have y equals x squared plus 1, but now we need to have x equals blah, 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 blah in terms of y. And my radius is going to be squared. So this is nowhere near as scary as it looks, right? All we have to do is take this thing here and make x the subject, and then get x squared, right? Just like over here, we had this thing here. This is y squared, right? So that's pi y squared. When we're working with the y-axis, if I can find it, we're going to need to square that. So let's look at how we can make x the subject over here. Well, we've got the curve as y equals x squared plus 1, which means that y minus 1 is equal to x squared. Now I could go further than that and go, well, that means that x is equal to the square root of y minus 1, and it could be the positive or the negative, but we know that we're only working with positive values. But then if I do that, I have to go back again and get x squared equals blah, 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 right? Because that's what I'm going to have in my integral. So we don't even need to bother with this step, right? Because we had x squared up here. I'm hoping some of you are actually watching this and that this is sort of making sense. That gives me the formula here. V is the integral between 5 and 1, and I've got pi times y minus 1. And I'm integrating with respect to y. So this is very easy to do now. We're going to pull that pi out the front, and we're going to integrate y and get half y squared, take away y for this bit here, integrated at my limits of 5 and 1. That gives me pi, and then 25 over 2 minus 5, minus 1/2, minus 1. Cleaning all of that up gives me this. I've got pi into 25 over 2 minus 5 minus 1/2 plus 1. Be careful not to make little mistakes here. I've got pi into 24 on 2 minus 5 plus 1, which gives me minus 4. So 12 minus 4 is 8. So my final answer is 8 pi, which is a good final answer. Or I could do 25.1. What are we doing? It'll be units cubed, whatever the units are. All right, so that's the volumes of solids of revolution question. I'm guessing, I haven't marked your papers, but I'm thinking quite a few of you probably marked that question up because I think rotating around the y-axis is likely to have thrown you off unless you had a pretty good understanding of that method. Hopefully now you do. This comes up all the time in AS, and once you've got it, it's really, really easy marks. Now the next question, there are a couple of ways to do it, and I'm going to do it using the chain rule, which I think you should all know. We first have to interpret it. We're given a curve, y equals x squared minus 2x minus 3. And we're told we've got a point moving along the curve, and the curve looks like this, right? So if we wanted to, we could rewrite that as x minus 1 squared minus 4 and quickly see that that's what it looked like. Right, a point is moving along the curve in such a way that at P, so somewhere on this point P, the y coordinate is increasing at 4 units per second. So you can think of that as dy dt, dy by dt. So per second, y is changing by 4 units, and the x coordinate is increasing at 6 units per second. And if you look at that, hopefully you'll see a chain rule relationship. We need to find the x coordinate of P. Now we know that y is equal to x squared minus 2x minus 3. That means that dy by dx is equal to 2x minus 2. So this thing here is my link between x and y. And this is saying per unit change in x, this is roughly what it's saying, per tiny, tiny unit change in x, what is the tiny, tiny per unit change in y? And it's 2x minus 2. So we're going to take this information, which tells us we've got t, how does t affect y, and how does t affect x? We're going to use the chain rule to put those two things together. So dy by dx is equal to dy by dt times dt by dx. And that's equal to dy by dt divided by dx by dt. And we know what they both are. Dy by dt is 4 and dx by dt is 6. So we get dy by dx is equal to 2/3. So what we're trying to find is the gradient. Where is the gradient equal to 2/3? But we know that the gradient is given by 2x minus 2. So we get 2/3 is equal to 2x minus 2. 8/3 is equal to 2x. So x is equal to 8 over 6, which is 4/3. So what that's telling me is that at the point on the curve, which is just here, then we're going to have dy by dt is 4 and dx by dt is 6. Okay, I think that's enough for one video. Please let me know if anyone's out there watching this and if this is making things better or worse. And also let me know if there are any particular questions in the exam that you desperately want me to do, probably tomorrow night. Thanks for watching.